Welcome to this explainer. We're diving straight into the totally fascinating world of physical computing and IoT prototyping. If you've ever wondered how everyday objects actually connect to the internet, like how a physical turn of a real-world knob magically sends data to the cloud, or how those automated alert systems actually work under the hood, well, you're exactly where you need to be. Today, we're zeroing in on how accessible open-source microcontrollers have literally revolutionized this entire process. It's really never been easier to build your own connected devices. So here's our game plan for today. First, we'll meet the ESP family. Then we'll tackle Project 1, Light Control, followed by Project 2, Sound Alerts. And finally, we'll wrap up with the big question: what will you build next? All right, Section 1, meet the ESP family, the brains of the operation. Let's get right into these low-cost, low-energy microcontrollers that make all this IoT prototyping an absolute breeze. Because, honestly, if you want to connect a physical thing to the internet, you need a brain to manage it, right? That's exactly what your ESP board is for. Let's look at the heavy hitters. When you put the classic ESP8266, the Node MCU, up against its newer sibling, the ESP32, things get really interesting. Both of these are just fantastic for prototyping. They're completely open source, and they're incredibly cheap. We're talking around $4 here. Plus, both have Wi-Fi built right in, so you don't need any clunky extra hardware to get online. But here's the real game changer. The ESP32 adds Bluetooth straight onto the chip right next to the Wi-Fi. And zooming in on the ESP32's specs, you really see why it packs such a punch. Designed by Espressif Systems and launched back in September 2016, this little board runs on TSMC 40nm processors. It's got 520 kilobytes of memory, sips a tiny 3.3 volts of DC power, and even has its own built-in antenna. Seriously, this tiny piece of hardware can talk to everything from a basic LED to complex cloud servers and even your smartphone. Moving right along to Section 2, Project 1, Light Control, bridging the physical and digital. Let's actually ground all this theory with a hands-on project. We're going to control a digital LED using a physical knob. Enter the potentiometer. This little component perfectly captures how we take physical movement, just like turning up the volume on your old stereo, and turn it into usable analog data. It's essentially an analog sensor. Kind of like a rheostat from high school physics, it lets us manually tweak the electrical resistance in our circuit, which directly changes the voltage flowing through it. And wiring this up, super straightforward. They're just 3 pins. We send our positive 5-volt power to terminal 1 and hook terminal 2 up to the ground. But the real action happens at that middle pin, which we call the wiper. We wire that wiper straight to the analog data pin on our board, pin A0 for this setup. As you physically turn that knob, the wiper moves, changes the resistance, and fires that variable data right into the microcontroller. So what does that data actually look like? Well, as you twist the knob, the analog value our board reads goes from exactly 0 at the very bottom all the way up to this highly specific maximum value, 1023. That's our raw data stream, constantly feeding into pin A0. Okay, but how do we actually use that data? It's all about the code. We want to automate our LED based on where that knob is positioned. So we write a really simple if-else statement. We say, hey, if the value crosses the 500 mark, so anything greater than 500, shoot a high signal to the LED and turn it on. If it drops to 500 or below, send a low signal and shut it off. Just like that, we've programmed physical automation. Now, to actually watch those numbers change in real time and make sure our knob is working, we use the serial monitor on our computer. We set the baud rate to 9600. That number is absolutely crucial. It basically sets the speed limit for the conversation between our board and the computer, making sure we accurately catch all those numbers flying in from 0 to 1023. Let's step it up. Section 3, Project 2, Sound Alerts, building an IoT alarmer. Because, if an IoT sensor detects a problem, like a sudden freeze or a door swinging open, you need it to yell at you. So we add a buzzer. Again, the setup is a total breeze. You just grab the buzzer's negative pin and connect it to ground. Then, take the positive pin and hook it right into a digital pin. We're going with digital pin 4 today. Now, you might be thinking a simple buzzer just does one annoying beep, right? No way. By writing a very simple iterative for loop, we can literally command this tiny little component to sweep through up to 30,000 different sound frequencies. This right here is why code loops are so incredibly powerful. You don't want to sit there and type out 30,000 lines of code. Instead, we use a for loop. We tell the board, start at 0, and keep looping until you hit 30,000. And here's the clever bit. We bump the frequency up by 10 every single time the loop runs, and we throw in a micro delay of just 1 millisecond. The result? A sweeping, rising siren effect built entirely from software logic. Actually, scratch that. It doesn't just have to be a siren. Once you get the hang of controlling tones and delays, you can program the exact frequencies of musical notes. You can literally teach this $4 board to play Happy Birthday for your friends. It's such a fun way to push the boundaries of what these little components can do. And that brings us to Section 4. What will you build next? The Maker Challenge. We've talked brains, inputs, and outputs. Now, it's over to you. So armed with these cheap, Wi-Fi-ready boards like the ESP32 and the exact logic you need to bridge real-world physical sensors with digital alerts, the sky's the limit. What physical object are you going to connect to the internet next? A smart plant monitor? An automated pet feeder? You've got the tools. Thanks so much for hanging out with me for this explainer, and happy building.